So let's look at the multi-input case, and then I have some examples to show you. So this was the previous example that we did, right? Now, if the system becomes a multi-input case, example 2, let's say, let's make it a multi-input case, 0, minus 1, minus 2, minus 1, x plus 0, 1, 2, and 1 times u. And let's say y is 1, 0, 1, x. So in that case, u now has now two inputs, u1 and u2, and you have this one, x1 and x2. Okay. Let me make it a simple question and say, let's design a state feedback controller to set the closed loop eigenvalues to, let's say, S1 is equal to minus 1, S2 is equal to minus 2. Okay? Let's look at that. So the first thing we ought to look at is the controllability, right? Is the system controllable? So it's a function of A and the B matrix, and it will be B, AB, right? So what should be the rank, right? It should be at least 2, because we have 2 rows, right? So you start with this, write the first one B, it will be 0, 1, 2, 1. And you can probably immediately see that it is already full rank because of this. But let's also write this, minus 2, minus 1, minus 2, minus 3. And we'll say this is rank 2, and therefore it is controllable. So no problem, I can design a controller. Okay? Characteristic equation. Now the difference is that I have 2 controls, and because I have 2 controls, U is now U1, U2, right? So therefore this V should be actually V1, V2. And therefore this R now is also R1, R2. So the pilot has now, if this was an airplane, has really 2 controls. One could be, let's say, the lateral control. One could be the longitudinal control, right? Now the order is 2. 2 states. What should the K matrix look like? Is it a vector or a matrix or a scalar? What should it be? It should be a matrix. What should be the size of the matrix? 2. It must be a 2 by 2, so that you multiply the vector of size 2, right, with this 4 by 4 and obtain another vector which is of size 2. Is that clear? Yeah. So okay, this should be then equal to now a matrix K11, K12, K21, and K22. How many unknowns do we have? 4. We had 2, now we have 4. Okay? 4 unknowns, 2 controls, 2 states. This is our problem now. Okay. Let's try to do what we have done before. And remember, the Ackermann's formula and the Bhaskara were only for single input cases. So this is now something different. We can't use Ackermann or Bhaskara. But we still have the same idea. We want to match the desired characteristic equation with the closed loop characteristic equation. So let's start with the desired one. The desired says S1 must be this one. So that means the desired characteristic equation should be here. The desired characteristic equation, let's call it, we called it alpha S, I believe, right? So because it's this is only possible if the system looks like this, if this is the desired characteristic equation. Characteristic equation. So why is it like that? Here S1 is equal to -1 and S2 is equal to -2. So this is the desired characteristic equation of the closed loop. It's -1 and -2, and it should look like this. So if you write this as an equation, you will get S squared plus 3S plus 1. Or plus 2, I'm sorry. Right? Plus 2. So that's your desired characteristic equation. So you want your closed loop system to look like this. Okay? All right, let's look at the closed loop equation, or the closed loop equation, and see if we can equate them. Let's see if we can equate these two. All right. Characteristic equation of closed loop system. Okay, let's look at the characteristic equation of a closed loop system. The way we found it was like this: Si minus A minus Bk should be equal to 0, and this is your, not really equal to 0, this is what we call the closed loop characteristic equation. Determinant Si equal to 0, -1, -2, -1, minus 0, 1, 2, 1, and k is equal to k11, k12, k121, k22. Right, that's that. So if you write this, it will look like this. You take the determinant, it will look like this: S plus K21. This is AKS. This is S plus 2K12 plus 2 plus 1 minus K22 plus 1, 2K11 plus K21 plus 2. Closed loop characteristic equation. Multiply this, you will get S squared plus, right, 2K12 plus K22 plus 1 of S plus K21 of S, and then you get a bunch of other junk, right? Plus 2K12, K21 plus K22 times K21 plus K21 minus that stuff. Okay, so that's equal to S squared plus 2K12 plus K22 plus 1 plus K21S plus all that stuff. A lot of values here. Okay, it's AK times S. All right. So what are we supposed to do now? We are supposed to take this and take this, and we equate them. AKS is equal to alpha S. And then find K. So what do you say to this problem? Well, first of all, this one here should be equal to this. 3. So that's equal to 3. This one here should be equal to how many equations do we have? Huh? 2 equations. How many unknowns? 4. Do I have a unique solution? No. Do I have a solution? Yes. How many? Many. Okay? So, here we are at a problem where I have a lot of options to choose from K in order to satisfy the characteristic equation. Basically, I have more solutions than I want. I mean, I really want one solution, but I have many solutions too. So, can I solve the problem? Can I design a feedback controller such that the closed loop system is here and here? Can I do that? If you were, yes, we can. There's a solution to this. We can find the feedback gains K. We can choose 4 feedback gains that will satisfy these 2 equations. Okay? So we can do it. It's not unique, but we can solve the problem. So from a engineering point of view, we are done. I mean, we have a solution. We can find a solution. In fact, I tried a few. One possible solution that I found at home, and you can try possibly others, is this one. This is one solution. 2 minus 1, 0, 0 is a solution. Another solution is K is equal to minus 1.5 minus 1.4 minus 1. Another solution. And that's another solution. In fact, we could safely say there are many solutions to K. Okay? There are many solutions to K. From an engineering point of view, that's perfect because I have a solution. In fact, I can now choose which one I want. I have more solutions that I want, and so on and so forth. You know, it would be much worse to say I don't have a solution, right? If the system is uncontrollable, I don't have a solution. That's of course a lot worse, right? Now we have a lot of solutions, and we just choose one, okay? And you as engineers, your job is to choose one of them. So. Question is, of course, which one should I choose, right? I mean, which one is better than the other one? I mean, they all satisfy the closed loop solution. They all now, the closed loop solution was supposed to be at -1 and -2. So the closed loop has now roots at -2 and -1, and all of these K values, they satisfy this, so it's good. Question is, which one should I really choose? Okay? So let me plot this again. And let's discuss this a little bit. X is equal to x1, x2, right? That's the output. The way this really happens is like this. You take x1, take x2. No, that's not really right. And you have 2 controls here. to R1, R2 minus K11, K12, K21, K22 times X1 and X2. This is what happens. Therefore, that is equal to R1 minus K11 X1 plus K12 X2. This is R2, sorry, it takes a little while, R2 minus K21 X1 plus K22 X2. In fact, we can maybe divide this up into two boxes. Do it like this. Right? Let me write this clearer. You don't have to erase it, but just to look at it clear. K11, K12. This is like that. Right? This is, I just divide this up now. In fact, this is a matrix, of course. They go together, but this one goes to U1 and this one goes to U2, and this is really what's happening here. Okay. And I have various conditions to do this now. So, let's look at the first solution that I found here. The first solution simply says K is equal to 2 minus 1, 0, 0. That's one solution of the problem, and everything puts it on this position. Now, if you have 2 minus 1, 0, 0, what does it mean? It simply means that there is no feedback for the second control. Right? I mean, K21 and K22 will be equal to 0, so no feedback here. And you adjust this feedback. So which means you can actually achieve this by only using one control. You don't need to have a second feedback loop at all. And this you could actually do with Baskura or Ackermann's now, saying that let's not use this second control, right? Let's just use only one control and see if we can still do the feedback loop. Can I still satisfy this? In fact, in the previous example, if you remember, you had one control. It was a second order system, and we were trying to place two of the roots randomly on the complex plane. So you can do it with one control. You don't need really two, right? I mean, and that was unique. So uniquely, you can do it with only one feedback control. You don't need two. In this problem, we have two, which means I have more choices now. Which means if I want to move the controls over here, part of it can go to control number 1, part of it can go to control number 2. If you want to move everything to the first control, you put this equal to 0, and you can only use this. I'm sure you can find a solution where these two are 0, and you have other numbers over here. Actually, you can do it here. Set these two equal to 0, right, in this. Basically, K11 and K12, set it equal to 0, and find the other two. You have two equations. Basically, two of them, if you set two of them, the other two you can find yourself, right? And then you have a unique solution if you set two of them yourself. Okay? So it's up to you. So you could actually say, let's remove this one, set it equal to 0, and use these two, basically one of the controls, or use this one, or you can use a combination of them. A little bit of this, a little bit of that, it will use it over there. Okay? Now we have a flexibility, since we don't have a unique solution. What does this mean? What does it mean in terms of a practical application? Listen. What does it mean in terms of a practical application? It means this. Now, I'm going to look at my system, and I'm going to make intelligent decisions now. One of the decisions will be, which of the controls do you want to use more? Right? Which one is more reliable, let's say? Another thing is, when you use only one of them, what's probably going to happen is that you will have larger numbers on these ones than this one, let's say. In that case, your second thought will be, which of these measurements are, say, more reliable? For example, here you're multiplying x1 with 2. On the other hand, here you're multiplying this one with a -1. So maybe you might say x2 is not a very good measured variable, so I would rather prefer this rather than this. I'm just making things up now. Okay? So you need to make a decision saying that this is more important, this is very measured well, maybe not measured very well. These controls I want to use more, this I want to use less. So you make that decision. I have more controls than I need. This is similar. Let me give you a practical example. Let's say you want to, let's say you have an airplane and you want to design a controller for the lateral movement of the airplane, for the roll movement. Okay? You want to design a controller for the roll. What does control the roll? The ailerons, right? So this is your control. It looks like two controls, but it's really one control because they work in symmetry. Okay? So when I say ailerons are 2 degrees, it means one is it's 2 and the other one is -2, something like that. All right? So you have one control. So you need one control to design a controller for the roll. No problem here. One control problem, one input problem. Let's say I put another aileron over here. Now you have how many controls? 2 controls. One is this one. All right, let's call it lambda 1. And the second one would be this one. And I'm telling you to design a controller for the roll. This is very similar to this problem. Both of them can be used to design the roll. Or you can use both in a combination. You can say a little bit of this, a little bit of that, will give you the roll. So it's up to you as a designer what to choose now. You can either say I'm just going to use this delta 1, or I'm just going to use delta 2, or a combination of them. Okay? So which one would you use here to control the roll anyway? Would you use a combination, or you just use one? Well, we use the one that has a larger moment arm. Typically, we use the one that's outside. Then what do you have the second one? Yeah, maybe you don't need the second one. But since you have the second one, you could now make much faster roll movements than previously, because if you didn't have them, you would only have these two, and you would have some roll moments. But because you have the second one, you have now much higher moments, and you can much higher turns now, right? So now it's up to you. You want to have fast turns, or you don't need that at all. Basically, if you have more controls, what happens that you have more choices now. Okay? And you have to make an intelligent decision which one you would like to use. Okay? Here are other things, other considerations. Let's say you don't have the second one. Okay? And this one has a a range, let's say, of plus minus 15 degrees or 20 degrees, let's make it simple, okay? Plus minus 20 degrees. With the maximum of these inputs, let's say minus 20 plus 20, you have a certain moment, okay? But let's say you really want to go much faster, you want to make faster turns, okay? So then you say, okay, this one will not have enough control movement. I need more control movement from here so that I can make that turn. So maybe I want to optimize this in such a way that this is working more, this is working less, this one here, but it will just help this one to make faster turns. And then you start optimizing these things. Okay? Now, you understand that there is some optimization needed if the solution is not unique. Understand that, right? The solution is not unique. You need some sort of an optimization in your problem to find the best valuable k. I mean, you cannot always sit down and say, okay, I'm going to increase this, to reduce this. And how are you going to do it anyway? I mean, the only information we have here is that the roots have to be at -1 and -2, right? So you need more information. You need some sort of an optimization. So these kind of optimizations are done in an area called optimal control. Okay? It's an area called optimal control. You're trying to optimize the k given certain criteria. For example, don't move U1 too much. Don't move U2 too much. Make sure X1 doesn't overshoot. Make sure X1 or X2 has a good steady state error. You come up with these new rules of optimization. This is, as I said, is an area called optimal control. Now, we will look at optimal control in a few weeks. Okay, after the exam, we will be looking at optimal control. And the most typical optimal controller that we are using will be LQR. Okay, it's called the linear quadratic regulator. This is the controller. This is an optimal controller. That's what we're going to look at. And here we can make decisions saying that move that control more than the other one. Make sure X1 is within certain criteria. X2 is not so important, let it loose. Okay? Because this one, this doesn't give much information of set closed loop eigenvalues at -1 and -2. It doesn't really tell you which states are moving more. Does it give you that information? It doesn't tell you X2 is more important than X1. It just tells you the LTI system as a whole has to have these closed loop eigenvalues. It doesn't tell you which state is more important or which state we need to take more care of. It also doesn't tell you which of these controls you should be using more or less, or which one is more important than the other one. It doesn't tell you that. It just tells you the LTI system as a whole should have eigenvalues where they are. And you have seen that if you have more control, you actually can do a lot more than just moving the eigenvalues to -1 and -2. We can do a lot more as controls engineers to move the eigenvalues to -1 and -2. We can do a lot more. We can make sure X1 is more important than X2. We can make sure this control is used more than the other one. Or we can all balance them out. We can tell which is more important and where to put more emphasis. Okay? And that is done all in optimal control. And this is what we're going to do in LTI control. Does it make sense here? So therefore, a unique solution, the way we did at the beginning of the class, is really possible if you have this one control, then you have this unique solution. But otherwise, it's not really unique anymore. Okay? You can do a lot of things.
So we cannot optimize single input?
No. There's nothing to optimize. There's one solution. If you just want to place the eigenvalues the way we put it. Right? You can't really. It's a 4x4 system, one control. You can move everything to one place, to the eigenvalues, And for that, you have one control. Therefore, your k value, your feedback gain k, is unique. If it was always unique, how much time do we have? Almost out of time. If it was always unique, it would be very simple, right? Anyone can apply the Ackermann's formula. Blah, 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 blah. Enter, boom, k value. But now, you need to make intelligent decisions here. Okay? That's why you need someone who understands flight mechanics and who's from the aerospace engineering department to make those intelligent decisions. And there's not one solution. There's not one unique solution to this. And therefore, there's a good controls engineering department, and then can be a bad controls engineering department. Everyone can move it to the eigenvalues that I just defined, but who's going to do it better in a more intelligent way? Okay? That's where you need good controls engineers with a good background in aerospace engineering. Okay? And that's why what we are doing is very important in this department. Because you are the ones who understand the physics and make the link between the physics and the controls problem. Now, on Wednesday, we will have our class, right? Make an effort to come to that class, because I will be showing you how I do this in MATLAB and Simulink. Okay? I will put up my computer. I wanted to do it today, but we didn't have enough time. So I'm going to put up my computer and show you how I design these things in MATLAB and how I run simulations in Simulink. Okay? And that will be probably your next homework, so make an effort to come here. It will be an application to what we have done so far, actually theoretically.